Okay, so welcome back. In this lecture, we begin really the second half of calculus. So up until today's lecture, we've talked about limits, which were needed to understand derivatives. And then basically everything we were doing was dealing with derivatives and understanding how we can use the derivative and what's its interpretation and things like this, right? Now, in today's lecture, we're looking at another part of calculus that, as we'll find out in a few weeks, is actually intimately related with the derivative. And that's this notion of an antiderivative and what's called integral calculus. So historically speaking, there were two branches of mathematics. There was differential calculus and integral calculus. And then with some theory building, it turns out that they're like inverses of each other and basically the same thing. So that's when it just became calculus. Okay. So we're starting the second half, and then we're going to work our way towards a theorem, not in today's lecture, but over the next few lectures, work our way towards what's called the fundamental theorem of calculus that relates these things together. Okay. So with this lecture, we introduced the notion of an antiderivative. So let's write down the definition of this first, and then we'll talk about it. So a function, capital F, is an antiderivative long word to write. It's an antiderivative of a function little f on an interval I when f, so capital F prime, so the derivative of capital F of x is equal to little f of x for all x in the interval I. Okay, so this is the fundamental definition that we'll be dealing with. And the best way to understand this definition is probably to begin with just a few examples. So let's look at like maybe I'll use f of x equals to 3x squared. All right, so this is just a simple polynomial function, right? So a question might arise, like, what is an antiderivative of that function? Okay, so we need to find a function so that basically we want this, like, find capital F of x so that the derivative with respect to x of f of x, capital F of x, is equal to 3x squared. So you said maybe I'll put like a lower subscript on it. So f subscript 1 is equal to x cubed. So does that work? Like if I take the derivative of that function, does it equal that? It does, right? It'd be 3x squared, and that's that, right? So notice the terminology here in the definition, an antiderivative, not a antiderivative. So this implies there could be more, right? So what would be another possible antiderivative of this function 3x squared? It's a lot simpler than that. In fact, this is like the closest so far. Like the exponent's going to be a 3 there, I suppose, right? Any other guesses? It's really easy.
Would it be 2x cubed?
2x cubed. Well, then if it was 2x cubed, what would the derivative of that be? It would be 6x squared. So that wouldn't be the same.
It would be square root of 9x to the fourth power.
Square root of, so square root of 9x to the fourth power. Well, this is really just 3x squared, but that's not the derivative, right? Right, you need the derivative to be that. Come on, guys. Like, what about this one? I'll label this subscript 2. So f subscript 2 of x is equal to x cubed plus 10.
What plus 10? Oh, yeah.
What happens when you take the derivative of this function?
It's just, it would be 3x squared.
And then that's 0, right? Through that piece. So that would work, right? What about, I'll make another one. So capital F sub 3, what about is equal to x cubed minus 2? What about the derivative of that? What's the derivative of that guy?
3x squared minus 0.
Yeah, 3x squared minus 0, so it'd just be 3x squared. So do you see what's happening here? It's almost like, in general, any function that looks like this, x cubed plus some constant c. And c could be negative or positive, it doesn't matter. So for any constant c. Right? If that's a constant, you take the derivative of this, that's going to go to 0, and this will be 3x squared. So anything that looks like that will satisfy this equation. So by the way, notice that, like, were we solving for a variable right now, right? Like, I said, like, solve this equation just now, I said by accident. Originally, I said find f of x so that this is true. But really, this is like an unknown, right? So we're solving for an unknown that's solving an equation. But we're not solving for like a value. What are we solving for? We're solving for a literal function, right? What functions satisfy this equation? So this is actually, this has a name. This is called a differential equation. I'll elaborate on that more later in lecture, but I thought I should just, because I accidentally said solve this equation, I have to say this now, that this is a differential equation. It's an equation that has derivatives and antiderivatives, a function and antiderivatives. And you want to solve that for the original function.
So basically, we're just going backwards.
Right, we're going backwards from differentiation. Now, in general, this example actually points out a theorem that about like this relationship between like the constants and the antiderivatives. Because as soon as you find like one constant, like I mean one function that's an antiderivative, then any other antiderivative is going to be like some constant addition or subtraction away from it. So that leads us to the following theorem. Okay, so it's kind of long-winded. It's going to take me a second to write. So if capital F is an antiderivative. Oh, I should say something real fast before I do that. This holds for any constant, right? So that means that there's infinite number of functions that are solutions to this. So a function can have an infinite number of antiderivatives. if you didn't already pick up on that from that C. Okay, so back to the statement of this long theorem. So capital F is an antiderivative of little f on an interval I. Okay. Then G, so capital G, is an antiderivative. I'm getting tired of writing this word already. Antiderivative of little f on I if and only if G of x equals f of x, capital F of x, plus C for all x in I, where C is a constant. It's some constant. We don't know what it is, but just is some constant. What this theorem is saying is basically what I just said out loud. That once you find one antiderivative, right, another antiderivative is also an antiderivative. Sounds weird. If and only if it's like just some constant value away from the other one. All my good black markers are gone. Okay, so I'm going to prove this because it's like we need to prove this. It's important enough about this concept that we should prove it. And because we're going to prove this, I need to kind of point out that there's an if and only if statement here. So in logic, if and only if statements are kind of like equivalencies in like logical statements. So and to elaborate on that, it's what's called a biconditional statement. So there's two parts to this theorem. It's hidden by that. So if G is an antiderivative of F on I, then G must equal capital F plus C for some constant C on I. So that's one part of it. The other part is that if G of X equals to capital F of X plus C for all X on I, then G is an antiderivative of little f. There's two directions. It's like if that, then that, and then if this, then that. That's what this if and only if means. So yes.
Sorry, I'm confused on the I section.
The capital I is just an interval. So we're just saying that capital F is the antiderivative, is one antiderivative of little f for all x on I. Because the definition is defined in terms of intervals, right? There are cases where like a function will be an antiderivative on like some intervals, but not all of them, right?
Wouldn't G always be an antiderivative because it's a part of X?
Not quite, especially if you have like piecewise functions. Like if you have piecewise functions, then over some intervals, the antiderivative will look like this. Over other intervals, it will look different. Right? So especially with piecewise functions. Like just to like kind of elaborate on that a little bit before I prove this, like if f of x is equal to like 3x squared if x is greater than or equal to 0, and x if x is less than 0, then this is going to, like, depending on the interval, this will have two different antiderivatives. Does that make sense? Like here, on the interval from 0 to infinity, the antiderivative will be x cubed plus c for some constant c. And then here, it'll be 1/2 x squared for the interval negative infinity to 0. Does that make sense? Why there's like, yeah, so. All right, so let's prove this. Now, when you prove biconditional statements, like if and only if statements, you have two things to prove. Like if the first part, then the second part, and then if the second part, then the first part. These are conditional statements. And I hope that all of you take discrete mathematics to learn about this at some time, or some type of proof course, because it is interesting to learn about the logic of these statements. But this is calculus. I can't go into that too much. I'm just going to go ahead and show you what the proof looks like. So, so what can we say? Which direction am I going to prove first? I'm going to first suppose that g of x is like this. So first, suppose, well, actually, it's like in the statement of the theorem, we're assuming that capital F is an antiderivative of little f. That's to be assumed, okay? So first suppose that g of x is equal to capital F of x plus c for all x in I, where c is a constant. Okay, we're assuming this, and we're going to show that g is an antiderivative of little f. Okay. So then, okay. Then g prime of x is equal to the derivative with respect to x of the right-hand side. Right? I just take the derivative on both sides. So g prime is equal to the derivative with respect to x on the right-hand side. But then, like, the derivative of capital F is just f prime, right? And then the derivative of a constant is just 0, right? But what do we know about f prime of x, capital F prime of x?
Principal zero.
Yeah, for all x in that interval, right? Yeah, I ran out of room, but let's just say for all x in I. So what does that mean? G prime of x is equal to little f for all x in I. So g is an antiderivative of little f. I would write that, but I ran out of room. So hence, g is an antiderivative of f on I. That's what we just deduced. We assumed this, and then we got that part up there. So next, we have to assume this, and then get this part here. That takes a little bit more work, but it's not too bad. Okay, so conversely, suppose g is an antiderivative of little f on I. Okay. So now we're assuming this part. G is an antiderivative f. And we want to, under that assumptions, get that that must be the case somehow. Okay. We're logically proving this theorem. Now here, there's a little bit of cleverness, I suppose, that we have to introduce. Next, define h of x equal to, not that, I want to do it in a different order. H of x is equal to g of x minus f of x, capital F of x. So define that, and then choose arbitrary A and B in the interval I with A strictly less than B. You'll see why I'm doing that in a moment. Again, there's like a little bit of cleverness here, I suppose. All right, so what did I do? I just defined some function called h. It's just the difference between g and f. Seems okay, right? And then I pick a and b and I with a strictly less than b. Yeah. Question?
But G is also.
No. G is just an antiderivative of little f. And capital F is another one, another antiderivative, because there can be a bunch of them, right? And if you think about what this what I'm setting up here. Earlier when I had all those antiderivatives, right? What were they? They were like x cubed, like let's just do like x cubed plus 10 was one, right? And then another one, so this will be like g, right? We don't know what it looks like though. Like we just know like g, right? And then we subtract off another one, capital F. And that, what did that look like? It was like x cubed minus 2 or something, right? So what's going to happen here is that like this piece and this piece are going to go away, and we're just going to be left with a number, right? Just some number. So this function here, hopefully, if the theorem is correct, hopefully this function is just going to be a number, a constant. So that's like the intuition behind why I would do something like this. If I can show that this is a constant, then I can do some things. Okay. So next, we have to recall that if a function is differentiable, then it's going to be continuous and differentiable, right? So that's continuous, they're both differentiable, which means that h is differentiable and continuous. So note maybe h is continuous and differentiable on the closed interval AB. Right, those are just numbers inside of I, right? A and B are inside of I, A is less than B. So we know that we can take the derivatives of these things here. Okay? So it's continuous and differentiable on that interval, which means we may apply this famous mean value theorem. So by the mean value theorem, there is some C in the open interval AB such that H prime of C is equal to H of B minus H of A divided by B minus A. That's what the mean value theorem says. There's some value C in that interval that equals the slope of the line connecting the endpoints over that interval. It's like that average rate of change on that interval. But what do we know here? Do we have any information to use? We have information here. I'm running out of room, but maybe I'll put it in blue, like right here. So H prime of C is equal to the derivative with respect to X. What's actually equal to this? We just take the derivative there and there, right? G prime of C minus capital F prime of C, right? But we've assumed what about G and capital F? They are antiderivatives of little f, right? So this is equal to what? Little f of C minus little f of C, right? Because the derivative is equal to little f everywhere in that interval. Same with that one, right? What does this equal? 0. So 0 is equal to that. Okay, so if this is equal to 0, then if we multiply both sides by b minus a, we'll get 0 is equal to h at b minus h at a, right? Which means that h of a is equal to h of b. An easier way to think about that is if you have 0 equals to this ratio, the only way that can happen is if those equal that right there. Okay? Now, here's the part that kind of goes back to what I was talking about over there, about like why I would set up that h. I wanted to see that if it was a constant, right? So since little a and little b were arbitrary, and we just picked any a and b in the interval I with a less than b, right? So for any two numbers we pick in there, this like those two numbers are going to evaluate to equal each other in the function, right? We get that h of x is equal to c. H of x is a constant function, right? No matter what a and b we pick in that interval, the same argument is going to show that h at a is equal to h at b. It's a constant function. This is for some constant c. Y'all, does that make sense? Yeah, question.
Can you define the C in the blue? Is that like a capital C, a constant, or is that
It's a capital C. Yeah. Those are little c's in the evaluation there. This is like some big C. And it's just saying that no matter what a and b we pick, we're always going to get the function equals at both evaluations. So it's a constant. But what does h equal? H is equal to g of x minus f of x, right? So here, I'm not going to be able to squeeze it in, but like this is equal to g of x minus capital F of x, and that's equal to c, right?
So h of x equals that.
Yeah, h of x is equal to this difference, right? So I just plug in what it is, and then I solve for g. g of x is equal to capital F of x plus c. And then that completes the proof. Because look where we ended up. There.
Will we have to learn the proof for this theorem for exam?
No, I only provide you with the proofs whenever I feel like it's important to tell you like why the theorem is true. You won't have to do this on your own.
Okay.
Unless
Thank you.
unless you're like a math major, and then in your upper level courses, you'll prove things that are similar to this. But there's like, it looks like a lot, right? But the reason why I know to do it is because like I had like courses that like kind of trained me how to walk through the logic, right? So that's why it seems like a lot, but it really, if you have that background, it's not that bad to prove. You just need that background to get there. And that's what like an intro to proofs course would do, or a discrete mathematics course would do. So all of that argumentation was just to like verify this theorem and give like a proof for why it's true. And it also illustrates like why people like use this mean, like think of this mean value theorem as like important, because you can use it in a lot of contexts to get things that you want. But now that we know about this theorem, we can kind of discuss it in context of like solving things. Okay, so actually I need to leave the theorem up there in order to write over there, because I'm going to reference this. So I can erase this part of the proof. It's all being recorded, so you'll be able to see it again if you want. So with this theorem, we know like there's like a way that solutions to finding antiderivatives will look like. Something plus a constant c, right? So in that statement there, so c is called the constant of integration. Okay. And G is the general solution of the differential equation f prime of x equals to little f of x. Okay. And unlike a lot of calculus instructors, at least at UHD, as we go on in the coming weeks, I'm actually going to emphasize differential equations quite a bit. It's like an entire field of mathematics, in applied mathematics especially. That people get PhDs in differential equations, like there's entire textbooks written on this stuff. And it's one of the most applied in the sciences, at least, fields of mathematics. Because a lot of times you'll, for example, like measure rate of change, right? Like you're measuring like something is changing at some rate, that's basically the derivative. And you want to know like what the antiderivative is, like what is the function that's producing this rate of change. But we'll talk about that in detail probably next week. So, okay, let's look at like a very simple problem to kind of introduce notation. So find the general solution of the differential equation dy dx equals 2. So what is it like a solution again? What's a general solution?
It's G of x equals
It's basically the antiderivative, the most base antiderivative of this function 2 plus a constant. And we don't know the constant, it's just like a constant, right? So now when considering like,
Wouldn't it be like 2x?
that's not the general solution. That is a solution, by the way. 2x is a solution. So what are we trying to, we're like in this case here, what are we trying to find? We're trying to say, find all y that satisfy that dy dx equals to 2. That's basically what this problem is saying. You found 1. When you said 2x, you found 1, but generally it would be 2x plus c. So I think this might be a good place to introduce notation, though. When thinking about this type of problem, the dy dx equals 2, it might help to maybe multiply both sides by the differential dx, the difference in x. That's what that means, dx. And we get that dy is equal to 2 dx. And then do something like this. So this is where the notation comes in. Y is equal to this. What is that, right? It's a new symbol. So in general here, what is that? Well, that notation is used in 2 different contexts. So if dy dx is equal to f of x, then y is equal to the integral of f of x dx. And I said it out loud, integral. So this is the antiderivative of f. So so antiderivative but it's also called the indefinite integral. Okay, yeah.
symbols of antiderivative, but the whole thing is called a.
It's so this all together, all of this thing together is the antiderivative and also the indefinite integral with 2 different names. They mean the same thing. And it's, if you're curious about what it is, it's an elongated S, which will become apparent why later in the semester. But yeah, so one nice thing about indefinite integrals is that we can factor, or not factor out, but we can pull out constants. And here, there's like a 1 right here, right? The 1. So So this is the antiderivative of f of x. That's what I should have said. So what's the antiderivative of 1? It's just x. So, but you have to remember your constant c. It's x plus c, really, right? So this is the general solution of this equation, and there's like a lot of notation going on, so you have to be careful. But the idea is really the same. It's just we're finding the antiderivatives. Okay. Now, with that being said, we can now move on to like actual, like interesting problem. Not interesting. Well, like yeah, more interesting than like that. Question.
So we're just going around circles to find.
Yeah, so like this is like so the whole thing here would be G. That's like your capital F of X. So like real quick, just like I'm curious if anyone can like do this. So like now that we have this notation, I can just ask you like what is that?
3x.
Oh, well, let's make it simpler. What about this?
We can take out X.
No, you don't take out constants. There's no constants anymore. X dx. Yeah, but
But there's no point on taking.
yeah,
X.
because there's always going to be a 1 there. This is asking you
X
what
squared.
I think I heard it.
It's 1/2 x squared.
Almost 1/2 x squared plus c.
Plus c, yeah.
So be careful. If you forget the c, it's incorrect. Because this is asking for like the general solution. It's asking for all the possible functions, and they'll look like that. So how did you get 1/2 x squared? I'm curious. So like, okay, we're gonna start making a table real fast. So the antiderivative of 1 is just what? It's just x plus c, right? The antiderivative of x, the general form is what? It's 1/2 x squared plus c. What about the indefinite integral of x squared dx? What's that going to be?
2x.
No, take the derivative of 2x. What do you get? You get 2. That's definitely not x squared. You want the derivative to be x squared.
Wait, so what would be the answer?
I haven't heard it. I haven't said it yet either. What's a function whose derivative will be x squared?
X.
Is it 1/3 x cubed
Almost. What are you
Plus
forgetting? Let's see.
plus c? Yeah.
Are we doing like a circle? Like you know how pi goes?
No, nothing like that. It's just thinking about the derivative.
I still don't get how x dx equals 1/2 x squared plus.
Take the derivative of this. What do you get?
It's because it's 2 goes to
Oh,
the
one
constant.
there,
and-
yeah.
And you're left with just x. That's right there.
Okay.
Let's try another one. What's the indefinite integral of x cubed?
1/4x to the 4th power.
Got it. So 1/4 of x to the power 4 plus c. Take the derivative of this. What do you get?
Yeah.
All right. Let's extrapolate this pattern. What's the indefinite integral of x to the power n dx, where n is an integer and n is not equal to -1. So that exponent is not -1. That's very important. But any other integer n up there, oh, no, not even integer, what am I saying? X where n is a rational number. Sorry, rational. So what's this formula right here? There's gonna be something.
Won't it be 1 by n plus 1 x raised to n plus 1 plus c?
That's it. So it's x to the power n plus 1 divided by n plus 1 plus c. I don't like the way you just looked at that. Take the derivative of this. What happens? Like this, like you can always check your answer, by the way. Like if you think that you have the indefinite integral solution, just take the derivative of it. You better get that, right? So if you take the derivative of this whole thing right here, you better get x to the power n. Do you? Let's like check it. So dx of x to the power n plus 1 over n plus 1 plus c. That's just 0, right? So we're just concerned about that. Use the power rule, right? Exponent multiplies down. So then you'll get n plus 1 times x to the power of what?
N.
N all over n plus 1. N plus 1 divided by n plus 1 is just 1. What are you left with?
X.
Hey, we got that back, right? So we're good. So this is probably one of the most, you're going to use this so many times in the homework. I'm going to actually like have you like do a lot of indefinite integral type things, but you'll be using that. Okay. So like, what's another one? So actually, we should just apply this real fast and make sure we understand before I write down some more examples. Like, so what's this? The indefinite integral of cosine x.
Negative sign.
So what's the derivative of negative sine x?
It's sine.
It's negative cosine. It's, yeah, this is just going to be sine x plus c. Right? If you take the derivative of sine x, you get cosine x. And the constant goes to 0. However, what about this? What's the antiderivative or the, yeah, so what's the indefinite integral of sine x dx?
Cosine x plus c.
It'll be negative cosine x plus c because the derivative of cosine x is negative sine x. So you want to cancel out the negatives. All right, so these are other rules. And in fact, I like highly encourage you in the textbook in this chapter to just like print or copy down that table that they list of like all the indefinite integral formulas. There's ones for like cosecant, cosecant squared, things like this.
I have a question.
Yeah.
So for every single time we solve one of these problems, we're just gonna, we all Do we just have to add plus C or add a number instead of? the C?
If it asks, if it is this,
Uh-huh.
if it's that, there's always a plus C. If it asks for the general solution to a differential equation, plus C. However, we're going to encounter a problem next time where you will have to find out what C is.
Okay.
And that is determined by what's called like an initial value. Right? You know the value of the original function at one point, which means that if you know that the value of the function at one point, then you can solve for that C, because like sine at that point equals a number,
Mhm.
and then you can solve for it.
Yeah.
But right now, we're just finding general solutions and antiderivatives. And indefinite integrals, I mean. So what about something like this? What about something like that?
2x's and 2.
I know. I want
So like,
something square, but I don't know what the square. would
well,
be.
actually, before how about just this? Like, let's just do this one first.
It would be.
It might help to rewrite it, by the way. That's the same thing, right?
Would it be 2x?
2x, take the derivative of 2x. What do you get? You get 2. That's not x to the power 1/2.
Like
It's like right in front of you.
it's like a half. No,
It's literally that.
Really?
Yeah,
Oh, yeah.
it is a rational number and it's not equal to -1. So it's just this. Just that. So what does it actually equal? Like, what would it look like in like the homework? What would the answer be? Because this is not like. What's a half plus 1? Another way of saying that is what? 3 halves. I can tell that y'all hate fractions. It's like it's not bad though. Like think about it. Like okay, that's a whole. That's a whole, and there's halves, right? So here's 1. How many halves are in there? There's 2 halves. 3 halves. 3 total halves. That's it. Don't be embarrassed. I didn't actually like get comfortable with fractions until I worked at a place called Mathnasium as a grad student, like tutoring kids with like fractions and things like that. So yeah, so this will become x to the power 3/2 over 3/2 plus c. That's definitely not how it would look in the textbook. It would look like this. 2/3 of x to the power 3/2 plus c. That would be the solution. You're dividing by the ratio, which is equivalent to multiplying by the reciprocal of that ratio. So dividing by 3/2 is the same thing as multiplying by 2/3. And then look, if you take the derivative, 3/2 times a half is just 1. X to the power 3/2 minus 1, it'll be that. You can always check it. Okay. What about something like this? So we have to like think about, now there's like a sum in there, right?
Wouldn't be the same as the bottom, but we would add plus sine x squared
Close.
plus. the
Yeah,
sine.
plus 2 sine plus c. So the way that we would deal with this is this is equivalent to the following. This is linearity of integration. The integral of the sum is the sum of the integrals. And that's because the derivative is linear, right? So if we're looking for the antiderivative and we have pieces like that, right? Then we know when we take the derivative of it, those pieces can go like that. Technically, it would need to be proven, but that's beyond the scope of Cal 1. Furthermore, well, we already know what that is, right? This is 2/3 x to the power 3/2 plus some constant, call it C1. Plus, now, that constant, like think about taking derivatives, right? We can always take the constants out. The same thing applies with integration. So we can just take that constant out. And then the like the indefinite integral for cosine x is just sine x plus c, right? And then I'll call it C2. But really, when you're doing this, like that's a constant, adding them together is a constant, right? So rarely will you see me like write out like the constants with each pieces. I'll just wait to the very end and then tack on a plus c at the end. Because C1 plus C2 is just C, whatever. All right, we'll do one more and then call it a day because I know you'll have an exam to think about. Now here, we have to be careful. We can't just like take the integral of like the ratio is not the ratio of the integral, because think about like how complicated the output of a derivative becomes when you're like multiplying or dividing things. It's not just like the pieces, right? It's like derivative of this times this plus the first one times the derivative of the second, or like with the quotient rule, the same thing, but a difference divided by the numerator, the denominator squared. So we can't take integrals of ratios like we can do with like addition or subtraction. It's different. However, when things look weird like this, it helps to kind of try to make it look like a sum, if you can. So we can split this ratio up as follows. Right? So then integral of the sum is the sum of the integrals. Notice that my dx here is going with both of the integral pieces. So a few things happened. I made that square root into 1/2 right there. And in that one right there, I brought to the top and I gave it the negative 1/2. Okay. That's just rules for exponents. If you bring something in the denominator to the numerator, the exponent becomes negative. So then here, there's like an exponent of 1 right there, right? So then x to the power 1 divided by x to the power 1/2 is equal to x to the power 1 minus 1/2. So what's 1 minus 1/2?
Negative 1. Oh, no, 1/2.
It's 1/2. Right, if that's like your whole thing, and you subtract out 1/2, you're left with 1/2, right? Like one way of thinking about it. So this is going to reduce to this integral here. Yeah. We know what the first one is. It's what, 3/2 x to the power 2. I mean, yeah, 3/2 x to the power 2/3. But other way, 2/3 x to the power 3/2. Like we've already done that one a few times. I'm going to wait to put the constant. No, maybe I'll just put the constant now. We haven't done this one yet. X to the power negative 1/2. But we have a rule for that. This power rule of integration, basically. Like that's like our n, right? So I'm just going to write it out up here to work it out on its own. This will be equal to x to the power negative 1/2 plus 1 all over negative 1/2 plus 1 plus some constant C2. So what does this become? Negative 1/2 plus 1 is 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So then we just take this and put it right there. So oftentimes when I'm dealing with these like integrals, sometimes they can get messy. I will pause right here, figure out what that is on its own somewhere else. And then I'll come back over here. So then this will be equal to 2/3 of x to the power 3/2 plus 2x to the power 1/2 plus c. Okay. All right, so that will be it for today's lecture. Go ahead and stop the recording.